Hey everyone. So I'm here today to talk about how we've scaled our data pipeline to route billions of events every month and maintain a very high level of deliverability. And this is especially in the face of third-party APIs, which might go down at a moment's notice. So for this talk in particular, I'd first like to talk about the constraints of the problem that we're trying to solve here. Then I'll talk through our particular architecture and how we started and how we've grown that over time as we've onboarded more and more customers. Finally, I'll talk about how we use microservices to run all this infrastructure in production. And then I'll finally wrap up with monitoring, how we actually make sure that everything is working together. So first up, what are the constraints of the problem we're solving here? Now, I'm going to hedge this talk a little bit since it primarily deals with the problems that Segment solves, but even though that's the case, a lot of these lessons can be taken if you're running an in-house ETL process or any sort of big data analytics pipeline where you're trying to fan the data out from one place to another. So let's make this a little more concrete. Suppose that you're running an online business. Let's say you sell running shoes as part of a website. If you're running this business, there are a few different people at your business doing different jobs. Perhaps you have customer support people who are responding to incoming tickets, or people are complaining about shipments or wanting to return certain items. You have salespeople who are maybe arranging those like really big sneaker deals, you know, like the ones that Steph Curry does or something like that. I don't watch sports really, but hopefully that was a good reference. Let's say you also have marketing people who, whenever you launch a new sneaker brand or a new campaign, they want to email all of your customer base and say, hey, we've got these new sneakers for you to come check out. And then finally, you have analysts who say, no, none of that. Just give me the data. I want the raw thing in SQL or some other data warehouse. So ordinarily, if you had all these places that you wanted to get the data, and each of them has a very well-defined workflow, you'd be using different tools. But the key insight here is that they all want the same data in every single tool. So what you do is you'd add little pieces of code for each one to get it into each tool. But that creates a problem, right? You end up with a tight coupling problem where you say, hey, whenever I want to add a new tool, I have to add a new piece of code. So how do we solve a tight coupling problem? Well, Java people will tell you, add a layer of abstraction. Boom. But in our case, that layer of abstraction is actually just Segment, right? It's a single API that sits in the middle. And you replace all of this custom code into each individual API with a single line where you send data to our API, and we'll fan it out into all of these other tools. And then, once you've decided to set the data, you can configure them with the flip of a switch. So for this particular problem, we need an API that can deal with thousands of incoming requests per second. It has to be able to track things like clicks, adding items to your carts, ad impressions, anything under the sun, and then it has to fan those out into tens and hundreds of thousands of requests to these external third-party tools. Additionally, the system is a little bit different than some of the other systems you've heard about today. And then that's it, that it needs to be real time. We're not talking a batch ETL process or a MapReduce job. A lot of these events that come into other tools actually perform triggers based upon real-time data, say when a user signs up or adds something to their cart. So we want to make sure that these things are delivered roughly under 10 seconds, but anywhere up to a minute is reasonable. We're not talking about dealing with finance or stock trading data here. And lastly, the system needs to be able to scale out in the face of hundreds of unreliable APIs. Now, there are a few golden metrics that we use to kind of hold ourselves to the standard of deliverability here. And these are what I'll use throughout the talk as kind of a benchmark for how well our system is performing. The first one is delivery rate. This is the rate at which Segment can deliver messages to third-party APIs. Now, you might be wondering, why on earth would this ever be under 100%? Right? Well, and there are a few reasons for that. The first off is that these partner APIs could go down at a moment's notice, so we're dealing with a pretty hostile environment. The second is that a client might, unbeknownst to the partner, be trying to send more data in than the partner can actually handle, in which case we'll either have to back up rate limit, or eventually drop the message. The second one is the end-to-end latency. This is the point from when the event is actually created to when it enters the third-party tool. And like I said before, we want to keep this below 10 seconds on average, though anywhere to a minute is probably reasonable. And then the last one, which isn't quite as much of a hard and fast metric, is our data fidelity. We want to make sure that if we're sending data through, that it doesn't get lost. And what I mean by that is, say if we're sending an email through, we want to make sure that that email ends up in all the different fields and all the different third-party tools, rather than dropping it at one point or another. So now that we have a good sense of the problem that Segment, or really any data ETL pipeline at a large company is trying to solve, I wanted to dive into the system architecture. In particular, I wanted to talk about where we started, and then talk about a few of the lessons that we've learned over time while scaling out this system. So to really set the scene here, I wanted to share a picture from our first office. And this is a little bit hard to see in the light, but calling it an office is slightly generous. This is one of the apartments out of which Segment was born. And as you can see here, our walls were covered with whiteboards. We had 4 $20 desks from Costco. We had about a 30-second commute walking from our bedroom to our living room. And over the course of the time, we had actually spent a long time building other products. Now, it might be unbeknownst to most of you, but we spent about 18 months building products that were totally unrelated to what we do today. And over the course of that time, we were starting to fail and really run out of money. So, as you might guess, when we launched this first version of Segment in about a week and a half, scalability wasn't quite the top of mind. So here's what we built it with. And these were all technologies that we were using at the time. And some of them we've still kept, and some of them we've moved off. Everything was Node, where we were able to work with JavaScript both on the server and client to enable us to prototype really, really rapidly. We were using RabbitMQ as our messaging layer in the middle. We used Amazon from day one, working on top of their EC2 and VPC infrastructure. And then we used Mongo and Redis as our primary data stores. And here's a rough architecture diagram of exactly how that all fit together. As you might guess, we presented an API to clients that was all written in Node. The API would process incoming events, and for each one, it would check out, given their API key, does this belong to a project that we're aware of? If it does, and everything checked out, we then fan it into RabbitMQ, which sat as our reliable queuing layer. And from there, Rabbit delivered it to 2 places. One is our integration workers. And the workers actually deliver messages into each third-party tool. And the second is our archiver. The archiver is just a bunch of flat files split by a particular project, which gives us a really good backup in the case that anything goes wrong with other parts of the code. And that's sitting on S3. So for the first part of our scaling, we had to scale this data collection API. Oh man, this is really hard to see. Well, I'll annotate here. So after about 3 months post-launch, we were doing a handy 80 requests a second, which really doesn't sound like much, though it felt like a lot to us at the time. And we were running about 3 API instances. And over the course of that time, we've scaled pretty significantly to about 13 to 15,000 per second of incoming messages per day at the moment. Though we're only running roughly 30 API machines to actually handle this load. So the question is, oh, thank you. That is beautiful. So the question is, what did we actually do in order to scale this system out, and what lessons did we learn over time? Well, there are 3 things that we did to actually scale this API. The first is changing from Rabbit to NSQ as our queuing system. The second is moving from Node to Go. And the third is making the edge entirely stateless. And I'll talk about each of these in turn. So first, moving from Rabbit to NSQ. For those of you who are familiar with Rabbit, Rabbit is a brokered queue, which means that individual Rabbit nodes are tracking exactly what sort of messages are being processed. And this worked okay for a while, but after a certain point, we started running into problems dealing with more messages than one Rabbit instance could handle. So we started coming up with a complex sharding scheme to split different Rabbit instances. But over time, this grew to be really operationally complex. So we eventually ditched the whole thing and moved over to NSQ, which is a distributed queue by default. And I'll talk about the architecture for that in a second. The second thing that this did was actually remove the AMQP protocol. And for any of you who have actually tried to implement the AMQP protocol or looked at the drivers for it, it is nuts. There's, believe it or not, a 7-way handshake in order to set up the connection to this queue, which is great if you need really, really high deliverability guarantees, but it makes implementing drivers a huge pain. So we actually built our own driver for NSQ.js running in Node, and it's worked pretty flawlessly, honestly, for the past 2.5 years. And finally, NSQ has been simple and rock solid to deploy operationally. How simple and rock solid, you might ask? 400 trillion messages, rock solid. And we're passing through roughly 100,000 per second right now. And the great part is, for most of this, we haven't had to do anything with NSQ. We simply boot more of them, and because they're distributed, they all take care of themselves. So how does this architecture actually work? Well, NSQ distributes you what they call an NSQD node. And this is simply a process which you publish to, and what's called a topic. You say, hey, I want to record that there's a click coming in, and then you have various channels which represent the fan out. Now the key here is that this NSQD is all one single program. So if you're publishing to it, you're writing to this program, and that program will first write to memory and then spill over to disk. It means that if you're running different consumers, the consumers each connect to each single one of these NSQDs. And so what this looks like in a network topology is you have a bunch of NSQs running independently. None of them have to know about each other. They simply just publish their metrics and their lookup addresses to the central set of lookup servers, which operate in a similar fashion to Mongo config servers. And then you have consumers, which can connect to either a subset or a full amount of NSQDs. And it doesn't really matter how many they're connecting to, so long as you're able to drain all these messages from one to the other. Additionally, NSQ recommends that you actually co-locate each NSQD with the publisher. So here you can see our revised setup for the API, and you can see that we have individual nodes that are running, and we have individual NSQ instances running right alongside them that then consumers will pull from. And I'll talk about why this was a significantly improved change for our scaling in a second. But even with this setup, we still ran into some issues. Now, if you're like me, you might have guessed, hey, I'm dealing with a bunch of website data. Chances are everyone's going to have more or less the same load pattern. We're going to have some spikes during the day. Weekends are going to be a little bit more light. Evenings, probably not that much traffic. Well, I was dead wrong. Here you can see metrics from 9 different projects on the Segment platform. And you can see that their load patterns vary pretty wildly. You have some which go down during the day, you have some which go up at night, and you have some which are really noisy because they're batching every minute or so. What ends up happening is your API servers get hit with very varied load. And this can cause problems, especially when the load is big. Now, here's what would happen when we were checking individual problems with our API servers. We'd see a single message come in that was relatively big, say a few hundred kilobytes, and then we'd see the entire server start grinding to a halt. Like we were seeing what should have been a 20 to 50 millisecond response time grow to 15 to 20 seconds. And we were digging into this and trying to figure out what was causing these issues. And eventually what we discovered was the event loop, totally blocking. Now, for those of you who are unfamiliar with Node, Node operates in a single-threaded event loop model, kind of like Netty. Though that one's a little bit different and supports multi-threads. Node essentially schedules some sort of work to be done, and as long as you're running synchronous code, the scheduler will continue just letting you run that code synchronously until you tell it, hey, I'm ready to be done, and you can perform some I/O now. At that point, you push more work to be done onto what's called the next tick of the event loop, and from that point forward, the scheduler will continue running until all of those have finished. It'll read the I/O and then perform the next batch of work. Unfortunately, in our case, we had some things that were very, very synchronous. One of these is just parsing JSON. JSON in Node is really quick to parse. The V8 parser is very highly optimized. but you can still run into problems, especially with big JSON bodies. Additionally, we'd often clone these requests in part of our functions to make sure, hey, that if I'm modifying some sort of nested field, it's not making it back to the original request or other functions that might deal with it. But this runs into problems. Say, for example, that your load balancer, hypothetically, or your queue use heartbeats in order to detect whether a server is alive or not. What would happen when we were dealing with this very nested JSON and basically blocking the event loop, the server would disconnect from load balancer and it'd disconnect from the queue that it was publishing to, meaning that we'd basically drop the data and nothing would get through. So we did two things here. One of them is that we actually switched this outer edge layer to use Go. Now, I'm not saying that you can't do the same exact thing in Go. It's just a lot harder. Go by default provides you with a scheduler between different Go routines, and of those, most things that you do within a single Go routine will end up yielding to the scheduler at one point or another. The second is that we actually split out this tracking API edge here on one condition. It'd be totally stateless. Now, in our case, messages come in. We do some basic validation around JSON and message size. And then from there, those messages are immediately queued. But the number one thing is that they don't have to talk to Mongo. They don't have to talk to the rest of the system. They don't really have to talk to anything. And what's great about this is that even if you have some sort of problem further down the line, like a network partition or a zombie apocalypse, no matter what, the rest of the infrastructure or this edge layer will stay up and will stay processing messages. It means that if we need to, we can scale to multi-region very easily. We can scale to more and more of these edge servers without having to worry about the rest of the infrastructure, knowing that those messages will just continue to queue and sit on their local NSQ instances. So to wrap this part up, we've scaled the API by making these edge nodes stateless, though I'll caveat this that this only works if you control the client as well. Otherwise, you're basically forcing a poor API onto all the developers who are building on it. We've used NSQ for simplicity and reliability, and we've used Go to achieve better parallelism. So remember, we started with this initial node API that was checking the database, and we moved to something that's a little more scalable in terms of our data collection. But I still haven't talked about the ingestion and fan-out layers, right? How do we get messages from our system into all of these different systems? Now, in our case, these are actual third parties, but you could imagine them at a fairly large company, these being internal teams, which actually just have different guarantees on their APIs. So for scaling the fan-out, I'm going to first talk about how we changed around our queue topology, how we decided to abstract everything, and how we sanely retry in the face of these failures, and discuss a few of the concerns around those. So let me talk first about queuing. Now, basically from day one, I'd always viewed queues as giving you flexibility, right? Let's say you're running a service, and the service has the ability to either go down, or it processes requests in seconds or minutes even. It doesn't get overloaded with any sort of like batch of messages because you have a queue sitting in front of it, right? They give you a little bit of leeway in how you're actually running these services. So needless to say, we run queues everywhere because they provide us a lot better fault tolerance. But what I hadn't really considered until recently is that queues also give you a form of scheduling. And let me talk about what I mean by that. Let's say you have some unit of work to be done, and say you're writing an operating system scheduler. You could represent that as a queue, where you're giving work to each individual core. And if you're doing this naively, you can just take work off of the front of the queue, give it to an individual core, take work, give it to the next one, take work, give it to the next one, and you actually get the highest overall throughput this way in terms of total work. But the problem is that you end up not being the most fair for certain things that are require higher priority, which is the whole reason that processes end up having priority. And it's something that these queuing systems don't give you by default. So instead, what if we could break up the work and actually logically separate queues such that we basically bin them up by priority or complexity? So we know that for all of these green tasks here, they can be accomplished really quickly, while the blue and gray tasks might take a little bit longer, but they won't block the green tasks. So let's tie that back to our example here. Initially, we started with just a single queue, where we'd have these integration workers, which were sending events to Mixpanel, sending events to Intercom, Google Analytics, maybe these 100 other tools. The problem, though, happens when one of these tools goes down in a way that causes each request to time out. Now, we want to be relatively generous with how we're doing timeouts here, because we don't want to try and abort the request too early. So we give maybe a 3, maybe a 10-second timeout to each of these tools to make sure that we're actually doing our best effort to deliver the message. But the problem happens when one of these tools gets slow, right? Then the integration workers are just spending all their time waiting, which is disrupting the fairness for every other integration. So what do? Well, we changed around the queuing topology here. Instead, we created a queue per each integration. That gave us better fairness between them and meant that integrations could fail independently. If you look at this graph of queue depth here, you can see that per each integration, some of them will go down and some of them will have spikes at various times. Some of them will even just be hit with various batches of data, but they won't affect one another because we have individual queues for them as well as individual workers for each one. The fact that we have individual workers means that we can also scale the throughput of those. So if we want to, say, send 50x the data for Google Analytics, we can run 50x the containers of any other integration. So our end system looks a bit more like this. And I'm simplifying here since there are a few hundred services running inside of Segment, but this can give you the gist. There's a tracking API, which is stateless, forwarding to an internal API, and then that forwards into individual queues, which workers take off and send to these third-party tools. Now, besides queues, the second thing that we learned very early on is to abstract everything. And I'll talk a bit more about what I mean by that. Now, my co-founder Ian often says, if you're building 150 of anything, you're probably going to want to err on the side of over-abstraction, because at that point, you don't want to have to change something in 150 different places. And so that's why we split things up. We keep every single integration that we run in its own repo, actually, so that there's individual commit logs, individual change logs, and a single release doesn't batch together updates from multiple integrations. Additionally, we've created a factory to actually generate these integrations, which is totally configurable via our own DSL. And for those of you who aren't familiar with JavaScript, I'll get to exactly how this works in a second. But essentially what you can do is create an integration just by passing it a name. You tell it which channels it's enabled on and what endpoint it's supposed to hit, and then a few of the settings that you need. One of the best things we did here as well comes down to this mapper layer. The mapper basically takes a certain JSON input and says, hey, I'm expecting this call to end up with a certain JSON output, which is in a sense what you really want to do with all of these different data transformations, right? You want to say, hey, I'm going to glue this one layer, layer A, to layer B. And eventually I'll get my format from one point to the other. And the holy grail of this is that eventually we could build some sort of visual interface or store these dynamically, maybe even on the fly, such that we are able to dynamically generate transforms from one service to another without doing hardly any extra integration work. Additionally, because this stuff is all abstracted into a core integration prototype, it means that writing new integrations is really simple. Pretty much all you have to do is say, I want to hit this particular endpoint with this particular query string or maybe this particular payload, and then all of the error handling is more or less handled for you. But on the subject of error handling, I couldn't talk about only that without talking about our retry behavior. And why it's important to talk about retries is these integrations fail all the time. If you think about, say you're running a service, and say it goes down maybe once a year, that's pretty good uptime in terms of nines, right? Not too bad. But in terms of the services that we're dealing with, if every service goes down on average once a year, that means we're dealing with downtime once every 2 days. So we have to be really smart about how we deal with all of these retries and do our best effort to actually deliver data. So we do two things when it comes to retries. We'll retry anytime the server indicates there's a problem on its end. These are all just 500 statuses. And then we also retry for rate limits. in the case where, say, a particular customer tried to batch too much data into a service, we'll back off and then send it later. Additionally, we'll try for any sort of network errors. For most of you, this should be pretty evident since network is definitely not reliable. But in our case, it's something that whenever we experience a timeout, network disconnect, couldn't reach a host, DNS failure, we'll then actually send the data again at a later point. And when thinking about retries, there's two key metrics to keep in mind here. The first is how long should you wait to deliver a message, which is honestly an open question. In our case, we decided we're going to wait up to 30 minutes to deliver a message. If after 30 minutes it's no good, then chances are that the API is down for an extended period of time. Secondly, you can consider the attempts to deliver a message. How many times am I going to try this API in order to actually get the message across? In our case, we decided 5 times is probably about right. If after that point in time, we drop 5 messages, then chances are that it's just poorly formatted for that API, and there's something else going on that's causing it to 500. And what this looks like here, which is relatively simple, is just an exponential back-off strategy. The key point is that we also add a little bit of jitter, roughly plus or minus 30% duration in the case of rate limits. So that way, if a customer is sending in data all in one batch, it immediately gets rejected. We're able to then spread out the delivery of their messages. I could talk about how this is all abstracted basically all day, but I'd like to switch gears here and talk about how we actually run this stuff now by using different microservices. And the key points here are that we've basically adopted microservices everywhere. Like most of you, we've used Docker to get better isolation, and we've done a lot to ensure that these are easy to boot. Now, I wrote a blog post a while ago about why microservices work for us. And most of the discussion out there around microservices revolves around scaling teams. Often it's the case where you have a software engineering team that's now 50, 100 people, and you need to figure out how you can actually split up those teams so they're not all working on the same code base and stomping on each other's feet. Additionally, people talk about microservices as being able to scale certain parts of your stack. Let's say we want to run more Google Analytics workers. If that's only one thing, then we can run 50 of those. Whereas if we're running total integration workers, then we have to scale those up, even though not all of them might be doing the work. I'd like to add a third point that's not often discussed as far as microservices go, and that's visibility. It turns out that most of the tools out there all center around the idea of hosts, processes, and network. And the problem here is that oftentimes it's very hard to figure out what's going on in a really big app just using those tools. I mean, what was the last time you fired up top or htop to figure out what exactly a 10 or 20,000 line program was doing? You probably don't. That's the whole reason that flame graphs exist, in fact. But let's suppose now, instead of running that 10,000 line file, you're analyzing a 100 line file that's running as part of its own process in a Docker container. What you can see here is it's immediately evident that this service has a memory leak. And it has a go routine leak. But it's very clear to figure out exactly what's going on here because there's only 100 lines in the file. Since the service itself is so small, we can forget about it most of the time, and then when it's having issues, we can pinpoint exactly where problems are occurring, which is what the nice thing that microservices have given us. Additionally, we split these microservices into what we call different clusters. So each cluster is separated by concerns. So in addition to monitoring at the service level, we get a little more insight into what particular hosts are doing. Of course, I couldn't talk only about the clusters without explaining what exactly the services look like. So this is a typical segment service. And I'll explain each of these in non-AWS terms as well. Route 53 is AWS's DNS service. This is indicating which load balancer we should point something at. Say if we connect to authservice.segment.local, we'll register a DNS entry for it. Additionally, every service will have its own load balancer. And that load balancer will point to particular instances or containers that are running on those instances that register themselves with the load balancer. What this means is that we don't need any form of service discovery. There's nothing like console or etcd running here. And admittedly, there's some performance overhead from that, and it doesn't work in all cases. Say if you have a driver which actually needs to connect to multiple instances for redundancy or failover. But it does work fairly well for most of our apps. I caveat this, that this will only work well for you if microservices are actually easy to boot, right? Otherwise, now you have two problems. You have a bunch of services, and it's really hard to orchestrate and run them. To do this, we use Terraform. For those of you who haven't used Terraform, it's pretty similar to Amazon's CloudFormation service. It basically describes your infrastructure in the form of JSON, or Terraform's HCL, I guess, HashiCorp configuration language. But basically what this does is it provides minimal work for a programmer who's trying to create their own microservice. In their case, they just say which cluster they want it to run on, the name and version of the Docker container, and then give it some memory and CPU. And boom, we're off to the races in terms of actually creating this thing and running it in production. Additionally, we built significant tooling around actually deploying these so that deploying them is easy, fast, and safe. Whenever you git push to a repo, GitHub will trigger a build in Circle, our CI tool. And from there, it will actually build a Docker image whenever the CI tool passes. From there, we can deploy via Slack or via CLI tool, which updates the image that's running in ECS, Amazon Scheduler, and then it pulls new versions of the code down from Docker Hub. In this way, it makes running new containers very easy and safe, and it means that we can roll back pretty much instantly since all of the old versions are also tagged in Docker Hub. Additionally, it means that we can run the same versions in stage as well as production. Lastly, I'd like to talk about monitoring, how we ensure that the system continues to run in production. Now, I like to say that the more surface area you have, the more visibility that you need into that system. In our case, it's really true. So since we have 150 different external touch points, which could possibly fail at any time, we require a lot of visibility and really invest in this religiously in terms of the metrics that we record. And so we keep track for every integration, delivery rate, success rate of the partner API, end-to-end latency, and any top errors that we see coming in. And like I said, we have a lot of these metrics here. But splitting each of them out into their own category gives us the ability to really figure out where problems are happening and find them quickly. Additionally, we keep a roll-up of these, so we can see for a particular integration or for the system at large exactly what's happening with any key area. And we built our own service toolkit to automatically record most of these metrics. They could be things like the duration that it takes to process a message, the CPU time, the number of Go routines, the memory. All of these things should be things that the programmer gets out of the box when they're building a service from day one. So as far as the big lessons for scaling our data pipeline, which hopefully you can use for your own internal data pipeline or if you're building your own ETL platform. If you control the client, you should try and make the edge as stateless as possible. This is something that honestly I hadn't considered was a good idea for the longest time. I always wondered about why Google Analytics or these other large-scale providers would basically 200 on everything, until I got to the realization that none of them care about supporting third-party clients, really. For them, they have a single client, and their number one concern is preventing data loss. So if your system operates under similar constraints, I'd recommend make the edge stateless, make it just a bin for incoming data, and build clients around that so that people can easily send data to it. The second one is that queues not only define service boundaries, where places can fail, but they also define scheduling and rate limiting. So it's worth thinking about when building your queuing topology, do I want everything in this queue to have the same priority, or do I want to actually split it out into possibly different workers or different topics? Third, you want to have microservices and workers if they can provide great visibility and scalability, only so long as they are easy to boot. It requires a significant investment on the infrastructure side, but it's paid off immensely for us in terms of providing better visibility into what the running system is doing. And finally, the bigger your surface area, the more visibility and metrics you need to provide. This is something that we've learned the hard way by not having good visibility into the system. And anywhere you can't ask, is the system working? What's going wrong right now? How many messages am I delivering? Is a case where you should record stats and metrics. I'd like to end this talk with a few open questions about what's next and what things we're considering, since this system itself is far from complete. The first one is just finding more search of fairness. And what do I mean by that? Well, right now we operate with fairness at the integration level, right? Messages come in, they get grouped into different integrations or third-party services, and from there, none of those will affect each other. We can spin up different workers, and essentially that system is fair. Where we don't operate with complete fairness comes down to how customers are sending data. Let's say a really large customer starts sending a giant batch of data. It could mean that a smaller customer actually has to wait for their data to come through at all. So we're considering various options there around either encoding the jobs within the queue format or coming up with some sort of internal scheduling system built into the queue itself that would provide good fairness on keys passing through the queue. The second idea that we've kicked around is moving over to Kafka. Like I said, NSQ has provided incredible scale out and very, very low operational overhead. But where it loses out comes down to replication. Like I said before, each NSQD is actually operating independently. And since these are backed by EBS, Amazon's scalable hard drive system, we don't worry that much about losing an individual node, except for the case where there's some sort of NSQ problem that writes bad data. Kafka would take care of this replication for us in addition to giving us crazy throughput. Third, we'd like to create a standard microservices toolkit that we're hoping to open source in Q3 or Q4 of this year. Ideally, this would give you everything that you need out of the box, like metrics, reporting, logging, error handling, everything if you're coming and creating a new service, such that you get all of these other visibility pieces for free. And the last one I want to ponder is the idea around custom data transforms. Right now, we control all of the code that's running in the system. But what if we didn't? What if customers who could support code, or partners, or really anyone? I'm aware that this is a total isolation and security nightmare, especially given the current state of running them as Docker containers. But if we could find a way to either give people an interface like Lambda does to run custom JavaScript functions or run custom containers, we could potentially scale out the system to support arbitrary integrations with customer data. So in that, I'd like to open it up for questions, and thank you all for coming today. Thank you.
Questions?
It's probably been a long 2 days.
Going once.
Okay, this is probably could be handled by customer support as we use you guys, but since I got you here. So we're just recently moved over to using Segment and looking at your stack because we were using another provider who just accidentally lost a day of data, which was not great. So my question is, with your stateless edge, what is your fallback for a failure at that level? I understand you're queuing with the NSQ, but what if, I don't know, the data center gets hit by a natural disaster or something?
Yeah, so currently all the NSQ nodes are backed by EBS, which provides pretty good guarantees in the case of failure. Since that's all stateless, what we could do, say if an entire region gets nuked, is then we can move to another region pretty easily because we have all of that code, we have the instances, and we can spin up the infrastructure basically at the drop of the hat for that.
So I guess my question is if the signal doesn't get off of the stateless edge, it's still persisted. So
It's still persisted, yes.
Somewhat stateful.
Yes. Oh, sorry. Yes, it is stateful, but only local to the machine.
Okay.
Yep, Elliot.
How's using Docker Hub in production been for you guys? We use them as well, and they go down all the time.
Yeah, we also have that problem, is the short answer. Eventually, we plan to move to the Amazon Container Registry, which should provide a lot better both security guarantees and reliability, because we have had problems as well pushing and pulling to them. For the most part, it ends up not being that big of a deal. But yeah, occasionally when our developers try to push a build, then we run into issues.
Anyone else? Yeah.
You didn't really talk about the Redshift integration that you guys have. Just wanted to expand on that a little bit.
Yes. So for those of you who are unfamiliar, recently we added support for warehouses to our platform. And what happens here is we'll basically bunch up all of this data on an hourly basis. That is where the archiver comes in. It will upload to S3, binned by each particular project that it's for. And then from there, we'll run an ETL step where we actually load it into the Redshift cluster. So I didn't talk about that as much since it's A, relatively recent, and B, we don't have quite the volume of traffic going through there since it's running on an hourly basis, and per each customer, it's only dealing with their Redshift instance versus some of these partner APIs, which are receiving thousands or tens of thousands of calls per second. But it is something that, yeah, what do you want to know?
So I'm curious, is there a custom API, say I've got my own events that are not going to Mixpanel or to Google Analytics, can that be routed through Segment into Redshift?
Yes. Yeah. Basically anything that you send into our API will batch up and then put into your data warehouse, whether that's Redshift or Postgres.